Okay, please take a moment and read through problem number 2, and then we'll get started with this. So we first need to draw a picture. This looks pretty similar to that first example that I had you get in your notes. We've got our river over here. And I've got a three-sided fence. We're going to call this X and that Y, which means that one's X. Can you take a moment, please, and figure out your primary equation? So even though this looks similar to the first problem that you saw in the notes, this is going to be a little bit different here because we're trying to not maximize or minimize the area, but in this case, minimize the fencing. Well, that's the perimeter. My primary equation should be P equals 2x plus y, which means our secondary equation, well, we're told that the fence will enclose 50 square feet of land. The area is our secondary equation. xy equals 50. We're going to need to plug this in, and I suppose we could solve for x or y. Why don't we solve for y? It might be a little bit easier. And I'm going to say y equals 50 over x. So our perimeter becomes 2x plus 50 over x. As far as finding the derivative goes, I think it's going to be a little bit easier if we do it as 2x plus 50x to the negative 1. And can you please take a moment, find your derivative, and then find the critical value or values. I'm just realizing that shouldn't have said p prime, that should have said p. We're going to get p prime equals 2 minus 50x to the negative 2. So p prime equals 2 minus 50 over x squared. I think I'm just going to set this equal to 0 and say 0 equals 2 minus 50 over x squared. 2 equals 50 over x squared. I'm going to cross multiply. 2x squared equals 50. Am I still on the screen? No, I'm not. Sorry. X squared equals 25. So x equals plus or minus the square root of 25 or plus or minus 5. Now, because x is one of the dimensions of this rectangle, a negative wouldn't make any sense, so we're just going to go with x equals positive 5. As for the domain of this thing, I know that x can't be negative, but in the same breath, I don't have a maximum possible value of x. If x is 50, y will be 1. But if x is 100, y would be a half. 100 times a half would give you 50 square feet for the area. X could be 1,000, and y would be 1/20th. There actually is no maximum that x can be, which means the candidates test isn't going to work here. Instead of using the candidates test, we need to use that global justification method that I think I mentioned in the first video, didn't tell you how to use it, but just mentioned it. Here's what we're going to do. Instead of trying to do an absolute maximum thing, or actually in this case minimum thing, I'm going to sort of approach this as if I was trying to find a relative minimum. But there is a little twist to it. I know that I have a boundary at 0. Parenthesis or bracket, it's not going to matter. And I'm going to put a tick mark at 5. And we're going to go and we're going to test our regions. We're going to plug into p prime. I'm going to go back to this version. If I plug 1 into p prime, so for this region, will it be positive or negative? Plug in 1, 2 minus 50 over 1, 2 minus 50, negative 48. That region's negative. Plug in 6, or really anything greater than 5. Well, 2 minus 50 over 6 squared, 2 minus 50 over 100 squared, 2 minus 50 over 1,000 squared, whatever. This is going to be small compared to the 2, so that's going to be positive. So I know that p is decreasing and then increasing, which means there's a relative minimum at x equals 5. However, I can do better than that. take a look at this. If I have some function that is decreasing for a while, and then increasing for a while, decreasing everywhere before this point, and increasing everywhere after, this relative minimum has to be the absolute minimum. Let me say that one more time. If you're decreasing everywhere before a particular x value, and then increasing everywhere after that particular x value, the relative minimum we found has got to be the absolute lowest point, the absolute minimum of the graph. This is the idea behind our global justification. Let me write this out. We can justify that P has an absolute max at x equals 5 because P is decreasing everywhere before x equals 5. But that's not quite good enough. We have to say why we know it's decreasing. Well, it's decreasing because P prime is negative and increasing everywhere after. X equals 5. And how do I know? Because P prime is positive there. This language that I'm using is called our global justification. And this is what I'm going to use to justify an absolute maximum or a minimum when I can't use the candidates test. Now, this is only going to work if when I make my number line, I have one sign before the number and one sign before my critical value and one sign after. If there was a place where it then changed back to negative, well, if I'm decreasing and then increasing, then decreasing, I can't judge anything from this. Only if you change from decreasing to increasing or increasing to decreasing and there's nothing else going on. And actually not just change from decreasing to increasing, but we're decreasing absolutely everywhere before x equals 5 and increasing everywhere after x equals 5. Now, I want to know the dimensions. Well, the dimensions are x equals 5 feet. Y is going to equal 50 over 5, so 10 feet. So I think the dimensions of my region will be 5 feet by 10 feet. And that's the answer to number 2.